Engineering 305, this is example problem 9.4, 9-4. Depends on whether you're looking at my little label or the problem label. What we have is a structural steel. Young's modulus is 29,000, 30,000, 29, fine, 29. Wouldn't want to be off by 3%. Whoa, 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 whoa. So that you have the number memorized all the time. But that's okay. Stainless steel is a little softer, just to let you know. It's 10 feet long, must support an axial compressive load. Axial compressive. Okay. As shown in figure 9.5, got the figure attached. The column has a 1x2 rectangular cross section. That's important, 1x2. So important that I wrote it down. 1x2 rectangular cross section. The left end is fixed, and it's pinned on the other end, and that will prevent rotation about a vertical axis. So I can't draw on that screen, and you can't see my mouse, but that's going to allow that to buckle upwards, but not in and out of, not in the Z axis. All right, you see how it won't. It's fixed in the Z. So So we got to solve this. Maybe we have to solve this twice. Maybe we have to start looking at our end conditions and solve it. But here's the problem. I can't tell which direction is the 1-inch direction and which direction is the 2-inch direction. It is not clear to me how that is shown, which is which. And this is a problem you will find on my tests too, that the problem isn't communicated very well at times. And so what do we do in this situation? Well, I don't know. I think you have to do it both ways. If this is real world, you're going to go back to your boss. You're going to go back to whoever gave you the problem and go, hey, this isn't enough information. I need more. I need more information. But okay. We'll solve it both ways. We'll solve it one way. We'll figure it out. Here you go. But they also want a safety factor of 2. So if you look at what I've got, I wrote down it's a 1x2. It's 10 feet long. I know my Young's modulus. I put that it buckles the hard way. When I looked at their picture, I thought that the vertical was the 2-inch direction. And maybe I'm wrong, and maybe we should do it both. I think we've got to do it both ways. But that's what we do. So, and then I needed a safety factor of 2, and I wrote down my equation. There's the equation that I'm going to work with. And now let's start cutting through our solution. Well, kind of. I want to show you something new, and that is, this is MD Solids. You've got it on your computer, and we've got all kinds of things we can work with here. It's so big. It's so big it doesn't even fit on my screen. I can't get down. Man, I can't. I was trying to see what's underneath the. I think there's a whole section on columns that I can't see because it's so big. But what I was really looking at was the section properties. Now that kicked up on my other screen, so I got to drag it over. And now I'm going to look at a simple situation, rectangle, and I've got a 1x2. I already put that in there from last time, and it saved it. And then when I hit the compute button, well, I can actually give it more information. If you look, I can give it elastic modulus, etc., etc. I'm going to compute, and a whole nother screen popped up again over on my other screen. Another window popped up on my other screen. The reason for that is because my other screen is the primary. And so now you're seeing all kinds of information. But what is kicked out, and I can't draw on it, maybe you can see. Oh, yeah, you can see where I'm pointing to. I've got an I max and an I min. So if I start working with those, do I understand what those are? It gave me IZ. So let's look at first. Let's slide over here. The way I drew that, 2 inches wide, 1 inch tall. So that's going to give me the minimum value of I. And that gave me up here moment of inertia and that because they're giving it up here because they're thinking you might be working with a beam. So that's the 0.166. And if we think about that, that would be 2 times, it's base height cubed divided by 12. So 2 times 1 cubed divided by 12, it's 1/6. So yeah, I get that 0.1666667. If I would go the other way, the maximum, that would be if I twisted the other way, that would be base would be 1 times 2 cubed is 8 divided by 12. So that's 2/3. And so that's where I get my I max. So I could go back here and I can say I is equal to 0.1666. Give me a better one there. Or 0.6667. Now, again, I'm not sure when they showed us that picture how they're really doing that. We'll have to think about that a little bit. But the other thing we've got going on is I've got end conditions. So what are my end conditions? Well, clearly in one direction, it's fixed pinned. Right? And in the other direction, realistically, see how that's holding it left and right? It's fixed and then guided. So do we have those boundary conditions? Oh, that one. So as I'm looking at that, so I've got, well, there you go. I've got fixed guided, that one, and then fixed guided L prime is equal to L over 2. And fixed pinned L is equal to 0.7 L. L prime is equal to 0.7 L. So it's either equal to 0.5 L or 0.7 L. I'm going to go with that. Oh, sorry. No. I want the longest. It's going to be the most dangerous when it's the longest. So I'm going with 0.7. And then I want that to be long and I want this to be small. And that's, again, I don't really know how they've got that oriented. And maybe they did it in a way that they changed. I don't know. But that's what I'm going to do to solve this. Is I want to pick the most dangerous way. So I'm going to say P critical is equal to pi squared E, which is 29 MSI, times I, picking the smaller one so that my load is smaller, divided by L squared. Well, that's, it was a 10-foot beam. Sorry, I should have had that out there. Pi squared 29. That's my equation from the top. And then my length was 10 feet long, so that's 120 inches times, times, and I'm picking 0.7 to make this as long as possible, and that whole quantity is squared. So now I do my calculator Olympics while you're on hold. All right, I don't know what was going on, but I had major calculator issues, and I don't understand I don't know where I was making mistakes, but here's where I ultimately landed, and that is if I did the calculation, I would get 6,754 pounds and a safe load of 3,375. Now, this is not what the book has. And I want to warn you, just because you should track along in the book as well. I mean, these are coming out of the book, so there's other ways to do them. And what they did was, in one approach, they used P critical is equal to pi squared, the 29 MSI. These are common to everything. And then they said that in one direction, where it was the long direction, it was the stiffer. So they went 0.66666666. But this was in the long direction, so then they used, well, and I'm not going to put 84. I'm going to put 0.7 times the 120 squared. And that's equal to 84 inches squared. And that gave them a result of 27 kips, which is, and then when they would also put in a safety factor, but see, this is P critical. P allowable was then 13.5 kips. And then they did it the other way, where they said, yeah, in the other direction, and I'll call it, this is 1, here's 2. In the other direction, still pi squared E 29 MSI. But then they said, well, now this is not as stiff, but it's not as stiff, but I'm using the shorter length. So in other words, they hooked it up the smart way. So this was 0.5 times 120 inches, and then that whole quantity is squared. And that gave them a P critical equal to, and now I had to, sorry. They got 13,200 pounds, not kips. And so P allowable, when you throw the safety factor in there, they got 6,500, well, 6,626 pounds. Now, that's because this was the stiffer way. The softer way had the shorter length, had the better end conditions. And that's what you would try to do. That's the way you would design it. I didn't necessarily know that, so I went more conservative and picked the weakest direction and the longest length. And that got me to a very low value. So, that beats the problem to death, right? Because we've solved it so many different ways, so many different places and times. So, ta-da! All right, hope you're doing well. Don't worry, more to come.